Alright, so let's solve the definite integral of 5 over x squared minus 1 dx. Now, this video is entitled to studying and practicing partial fraction decomposition. So, the easiest way to solve this problem is, well, like I said, partial fraction decomposition. So let's take this entire fraction and let's go ahead and rewrite this as this. So I'm going to say 5 over x squared minus 1 is equal to, now remember, partial fraction decomposition, however many terms you have in the denominator is how many terms you're going to have as separated fractions. So in this case, we can rewrite x squared as x minus 1, x plus 1, right? So we have two multiples in the denominator, so we're going to end up having two fractions over here separated. And then on the numerators for both, we're going to have two unknown values right here, two unknown constants, which we're going to have to solve for. So I'm going to go ahead and write x minus 1 here and x plus 1 here. Now it honestly doesn't matter what order you put them in, as long as you solve for a and b correctly, and if you do, you should get the same result at the end. So let's go ahead and solve for one of these constants. That way we can solve for the other constant. Now, let's go ahead. How are we going to go ahead and do this? This looks a little bit intimidating, right? Because we have two unknowns that we're trying to solve for. Well, I'm going to go ahead. I don't really like fractions too much, so I'm going to try to get rid of these fractions. So I'm going to multiply both sides of the equation by x minus 1, x plus 1, like this. And then the same thing I'm going to do on this side. So I'm going to multiply it by x minus 1 plus x plus 1 squared. I'm just going to write it as x squared minus 1. All right, and then we're going to see that these two cancel out. And then over here, we're distributing, right, in here. So let me write the left side of the equation. So we have 5 on this side is equal to, now if we distribute x minus 1, x plus 1 to a, we know that a is just going to have the term multiplied x plus 1. Because x minus 1 in the denominator cancels out with this multiple, plus b times the multiple x minus 1. All right, so let's go ahead and solve for b now. Or it doesn't matter, we can solve for either or. I'm going to go ahead and solve for b first. Now, how do we do that? Well, we want a to be 0, right? Because we don't want more than one unknown. So let's just say x is equal to, now we want to make sure that a is equal to 0. So what's going to make a equal to 0 depending on what x value we use? Well, if we say x is equal to negative 1, we're going to see that this is going to cancel out, right? That's going to be 0. So if we say x is negative 1, this is what we're going to have. In the case x is equal to negative 1, we have 5 on this side. Then this is going to cancel out as we just witnessed, plus b times when we plug in x is negative 1, so minus 1 minus 1. And we see that if we solve for this, b is going to be negative 5 over 2. All right. So I'm going to go ahead and underline this to keep it in safekeeping. Now let's solve for a. Well, can we do the same thing that we did for b? Well, yeah, we can. If we set x equal to 1, that is, we can see the same thing happens here. That's going to result in 0. So we're going to have 5 is equal to 2a. Therefore, a is going to be 5 over 2. All right? So now we have solved for a and b. So we can now substitute, instead of doing this to make it a lot easier to solve for the integral, That's the purpose of doing this, is to separate into multiple fractions where the integral process or the integrating process is a lot smoother and a lot simpler. All right, so we're going to end up having from 2 to 7, right? Now a, we said, is 5 over 2. So I'm going to write 5 over 2. Now I hope you don't get thrown off if I just pull out 5 over 2 over here like this, because it can be treated as a constant. Remember, we said a and b are constants, so treating them as constants is actually something that we want to do for integrating. So x minus 1 over here, that's for our a term, times dx, and then plus, right, the integral of negative 5 over 2, that's our constant b, times 1 over x plus 1 times dx. And the bounds are from 2 to 7. All right. So let's go ahead and do this. So let's go ahead and solve for this integral. So we have our constant sticking out here off to the side lines. So 5 over 2. Now what's this going to be? Well, the integral of 1 over x minus 1 is the natural log of x minus 1, right? And let's evaluate this at 2 to 7. And over here, we have minus 5 over 2 off to the sidelines. And we're going to have a natural log of x plus 1 when we integrate. Evaluated from 2 to 7. All right, so let's go ahead and evaluate this. So I'm going to leave 5 over 2 out here. So I'm going to just say this is 5 over 2. Natural log of 7 minus 1. So that's the natural log of 6 minus the natural log of 2 minus 1, which is natural log of 1. And we know natural log of 1 is 0, right? So let's go ahead and say that's 0 minus 5 over 2 times the natural log of 7 plus 1, that's 8, minus the natural log of 2 plus 1, that's 3. All right. And we can go ahead and simplify this, right? So I'm going to say that this is 5 over 2. I'm going to pull out or factor out a 5 over 2. So we have natural log of 6 minus whatever this is. So natural log of 8 minus natural log of 3. Now remember the properties of logs. You can, when you subtract two separated logs, you actually can combine them and use division properties. So it's going to be equivalent to natural log of 8 divided by 3. And if we simplify this even further, we see that this is 5 over 2. Now natural log of 6 minus natural log of 8 over 3. So if we divide those two terms, we get that. I'm going to open up an absolute bracket here. So 6 divided by 8 over 3. So that would be 18 over 8, right? And you can simplify this fraction, of course, too. So 5 over 2 of natural log of 9 over 4. And this should be our answer.